All right, this time for sure. Hopefully. Probably. This should be the last video for Unit 7 with thermodynamics. We're going to talk about electrolysis. This is where we use electrical energy to create a chemical change. You can think about this for things like recharging a battery in your computer or in your phone, or sometimes we'll electroplate one metal onto another, say to coat some iron in chromium so it doesn't rust as easily. And this is going to involve using a number called Faraday's constant, which says there are 96,485 coulombs, which is just a unit of charge. So this many units of charge in 1 mole of electrons. So here we say if a current of 5 amps is applied to zinc plus 2 solution for 15 minutes, how many grams of zinc will be plated? And an amp is really just 1 coulomb per second. It's an amount of current, how much electricity is flowing through. So we can look here and see that zinc plus 2 will pick up 2 electrons to become zinc as a solid. Now 15 minutes, and we want to get that into seconds, so 60 seconds is a minute. And we said we're going at 5 amps or 5 coulombs per second. Faraday's constant says 1 mole of electrons is 96,485 coulombs. And we need 2 moles of electrons to get 1 mole of zinc. Then 1 mole of zinc is 65.4 grams of zinc. So in 15 minutes, at a current of 5 amps, we will plate out 3.1 grams of zinc. If you look through, you can see this is really just a stoichiometry problem. Minutes cancel minutes, seconds cancel seconds, coulombs to coulombs, moles of electrons, moles of zinc, and we're left with grams of zinc. So here's another very similar problem. What I'd like you to do is read it, well, I'm going to read it, and then pause and try for yourself, and then we'll check it on the next slide. So if a current of 2.5 amps is applied to a copper plus 2 solution for 30 minutes, how many grams of copper will be plated? Go ahead and pause the video and try it for yourself. Actually, before we go on to the next slide, I caught a mistake on my previous one. I didn't divide by the 2 moles of electrons. Hopefully you saw that mistake, so my answer is actually half as much. Now, this next problem is so similar to this one, I actually copied and pasted the slide, which is part of how I caught my previous mistake. So instead, we have 2.5 amps and 30 minutes, but it's still copper plus 2 electrons makes copper. So most of the setup is the same. The only real changes here are the time, the current, and the molar mass of copper. We still go minutes to seconds, seconds to charge, charge to electrons, electrons to moles of copper to grams, and get 1.5 grams of copper. You can see the answer is essentially the same once we get to significant figures, because copper and zinc are very similar in masses, and we have half as much current applied for twice as long, which means we still moved the same number of electrons. And so we ended up with about the same mass of metal. If you'd like some additional explanation or practice on these things, here's a good video link for you to follow. Now our last thing, let's tie all of these pieces together. Electrical potential measured in volts is work measured in joules that we've talked about before divided by charge in coulombs. This means that work is, now the negative is just because of the direction here, but charge times potential. Q is the amount of charge in coulombs. E is the potential. Now, charge is also number of moles of electrons times Faraday's constant. So we can say Q equals NF. Which then means we can say instead of work, which delta G is also the same as work, equaling negative Q times E, If we plug in NF instead, we can say delta G equals negative NFE. So this shows that Gibbs free energy and cell potential are directly related to each other. And this is actually a way that we can experimentally find delta G. This gets us to the Nernst equation, which is one that I'm guessing your maybe parents or older siblings just remember this name, even if they don't remember the equation itself. From before, we had delta G equals delta G naught plus RT ln Q. That's from our Gibbs free energy screencast. And we just on the previous slide said delta G equals negative NFE. So if we plug negative NFE in for delta G, we get this whole big honking monster. But if we divide the whole thing by negative NF, it's not nearly as scary looking anymore. We can say the cell potential at any conditions equal the standard cell potential minus some constants, and we also have temperature and N in there, times the natural log of Q. But if we're at 25 degrees Celsius, R's a constant, F's a constant, we can plug all those together and instead say E equals E naught minus, this is just the number you get when you put RT and F together, divided by the number of moles of electrons, and then they decided to switch to the log of Q, which is perhaps because when they did this, it was a long time ago and calculators weren't very easily accessed, and doing log base 10 of concentrations was probably easier by hand. So this is still the equation that we're going to use, and it'll work just fine. We just changed the base from base E to base 10. So here we have an example problem. We have aluminum reacting with Mn plus 2 to make Al plus 3 and Mn as a solid. The standard cell potential is 0.48. But you can see we have some non-standard concentrations. So you're going to use the Nernst equation to solve this problem. In case you haven't picked up on it yet, again, I would like you to pause and try for yourself. When you're ready, we'll go to the next slide. Okay, again here all I've done is copy over the information. We have the same reaction, 2Al plus 3Mn plus 2. Makes 2Al plus 3 plus 3Mn. E naught of the cell is 0.48 volts. Here are our concentrations. We find Q the same way we would find K. So we've got Al plus 3, and there's 2 of them, so it's squared. And Mn plus 2, and there's 3 of them, so it's cubed. Notice we're ignoring the solids because they don't have concentrations. So Q is 1.5 squared over 0.5 cubed, or 18. Here's our Nernst equation. So we'll say E equals E naught, 0.48, minus 0.0591. Now here we're moving 6 moles of electrons, because if you look, 3 times a plus 2 charge means that's 6 electrons over here, right? And 2 times a plus 3 charge means there's also 6 electrons over here. So in one whole set of this reaction, 2 moles of aluminum react with 3 moles of Mn, 6 moles of electrons are going to react. So we've got 6 moles of electrons times the log of 18, which gives us 0.467, or to 2 significant figures, 0.47. Notice, E of the cell didn't really change by very much. It did change, and it changed in the direction we expected. If we increase the concentration of a product and decrease the concentration of a reactant, remember they would have both started at 1, both of those things will shift the equilibrium to the left and decrease E of the cell, which that's what happened. It just didn't happen by very much. Finally, I want to leave you on a review question here, or a review task maybe perhaps. Draw a complete cell and calculate the standard cell potential between copper and aluminum. It's copper plus 2, not copper plus 1. Label the anode, the cathode, the electrodes, cations in solution, and anions in solution, it really should say there. The direction of the electron flow and the direction of the salt bridge ion flow. Then use the Nernst equation and calculate the potential if the copper concentration was increased to 3 molar. Leave the aluminum concentration at 1 molar. Now, I'm not going to work through all that with you. I want you to do it yourself, and if you have questions, you can go ahead and ask me either in our Hangout session or in office hours. All right, this is the end of Unit 7 Thermodynamics. Hopefully you've picked some stuff up. You can go back and work through the problems again if you like. There are also the linked videos in the slides themselves.